Okay guys, in this video lesson we're going to take the next step in terms of looking at this idea of gravitation and planetary motion, and we need to start talking about Sir Isaac Newton again. Okay, so up until this point, using the stuff that Kepler was talking about, we were able to track the relative positions of periods and radius of planets. What Newton did for us is he made the link between the gravitational pull that pulls objects to the surface of our planet, like an apple falling from a tree, or anything that deals with our projectile motion stuff we've already talked about, to apply that to planets. Okay, so he provided that link saying, hey, wait a minute, the same forces that cause things to fall to our planet are the exact same forces that put things into orbit. Okay, and from that he was able to actually determine that ratio of forces that exists between two objects when they pull on each other. Or basically, he was able to define and determine this universal law of gravitation. Okay, so if we look at the actual universal law, the law says that all bodies in the universe attract each other with a force that's proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, that's a lot of words that combine together to make a nice equation for us. So let's break it down and actually build the equation from that. Okay, so first of all bodies in the universe attract each other. That means everything. Okay, if you have mass, you have gravity. Okay, it doesn't matter if you are a moon, if you are a city bus, if you are a speck of sand, or if you're an entire galaxy, you have gravity. Okay, that is attraction. So gravity is always an attractive force. It's not repulsive, it always attracts. Okay, it's proportional to the product of their masses. So if we multiply the two masses together of any two objects, that's our first piece. Inversely proportional to the square of the distance. So now we're going to be inverse. We're going to divide by the square of their distance. So the farther away you get, the weaker the force is. All right. If we do all that, we find out that the proportionality, this little symbol here, designates some proportionality for us. It's not equal yet, it's just proportional. Okay, the force that we feel is proportional to the mass of each object multiplied together divided by the radius, okay, squared. Which means if we have a bigger mass, more force. If we have a smaller mass, less force. If we get closer, more force. If we get further away, less force. Okay. In fact, using this proportionality, we can take a look at some different examples. So if this is our normal force between this massive object and this massive object, if I double the mass here, I get twice the force. Even though this one is the same, okay? And the force they both feel is the same. Go back to Newton's third law of motion. If we have the double mass here and double mass here, well, 2 times 2 is 4. If we triple the mass here and leave the mass the same, it's 3 times, okay? You're going to notice that the effect of gravitational force is greater when we deal with distances. Okay, again, same scenario, but now we double the distance. Well, if you double the distance, that's 2 squared, or it's 4 times less force because it's in the denominator. So we get 1/4 of the force. Okay, if we cut the distance in half, okay, so it's 1/2 squared. Okay, 1/2 squared, or basically it's 4 times the force. Okay. And we can even combine. What if we had double the mass of each thing and double the distance? Well, double the mass of each thing is 2 times 2 is 4. Double the distance was 1/4. So 4 times and 1/4 bring us back to being the same amount of force. Okay. So take home here is that small changes in the radius have bigger effect on the force than small changes in mass because of the squared value inside there. And it's an inverse square kind of scenario, where the further away you get, the weaker it is, the closer you get, the stronger that is. Okay. Now, problem with Newton was he wasn't able to find the actual constant that made them equal. So he could solve for the proportionality, but not the actual numerical value. Okay. So Cavendish did this for us. Okay. So what Cavendish did is he set up an experiment where he had a beam or a line or a light of some sort pointing towards a scale or a grid. All right. And he had it hanging from a wire with 2 masses on the end. All right. And then what he did was he would spin another set of masses on either side of that and just move them, not fast spin, like a slow just rotation. And as he would move them, what would happen is the torque on this cable would pull against the gravitational pull between these two objects. And as a result, as you had more gravity pulling this sphere, this green sphere this way, and this green sphere down this way, it would bend this cable or twist this cable, causing the beam to offset from the original position. Well, you do that with different masses, and you're very meticulous about doing this, you can develop an entire data set on how much this rope twists based off these different masses. And from that, you can determine more than just a proportionality. You can actually determine the overall equality between those. Okay? So this little experiment here allowed us to jump from being this proportional to being equal. Okay? And the only difference in our equation now is the constant. Okay? So he was able to determine the first rendition of this constant with pretty good accuracy. Okay, so we call this a universal gravitational constant, big G. All right, 6.67 times 10 to the negative 11th meters cubed per kilograms times seconds squared. The reason why this label is as such is when you put a constant into an equation, all of your units have to cancel out properly to equal the gravitational force here. Okay. This is what's allow us to take the mass times the mass divided by the radius squared times this to tell us what the force will now equal instead. All right, so that's what we're looking for. So let's do a little bit of work with this, okay? What is the mass of our planet, assuming 1 kilogram mass is accelerated at 9.81 meters per second squared on the surface, okay? The radius of Earth is 6.37 times 10 to the 6 meters, okay? So looking at this, the first thing we have to do is identify our variables in our equation. So here's our equation. We know G. We know the mass of the object. We don't know the mass of the planet. And we do know the force. Okay. Now if we look, the problem only gave us the acceleration due to gravity, or they gave us little g, right? So they said that this is little g, but we also know that force is mass times gravity. So if you take 1 kilogram times 9.81, right, that'd be the mass in 1 kilogram, the acceleration of gravity is g. Multiply those together, that would give us the force, okay? So that's where we came up with this force here of 9.81, all right? Now that we have this, we can plug it into our equation. So rearranging this equation to solve for mass, we get the force times the radius squared divided by g divided by the mass of the object, okay? Plug these in, and we come up with an answer of 5.97 times 10 to the 24th kilograms, okay? So that's the mass of our planet. Right? It's interesting. All we need to know is the acceleration of gravity and the radius of our planet, and we can figure out its mass. Okay? We don't measure the mass of a planet directly. We use things like this to solve for those masses based off of the more simple data that we can collect. All right? So a direct kind of application of this law of universal gravitation. How about this one? What is the gravitational force on a 91.7 kilogram object on the surface of our moon? Okay, so we need some more information again. Radius of the moon is 1.737 times 10 to the 6 meters. The mass of the moon is 7.3 times 10 to the 22nd kilograms. Okay, so again, we know the g, we know the mass, we're looking for the force. Okay, so we're missing that information here. All right, so going to our equation, let's plug our information in here and then solve for that force. So in this case, we don't need to rearrange it. We have big G, the mass of our object. We have the mass of the moon. We have the radius of the moon squared. Plugging that stuff in, and we end up with a force of gravity of 148 newtons. Okay, this is a force. Gravity is a force. So just like all forces, it is measured in newtons. Okay. We're going to end the video lesson here, guys. There's definitely homework for you guys to do to practice working on this equation more, but also make sure that you are in tune with this idea of the relationships. So be ready to answer questions like, what happens if you double the mass? Or what happens if you cut the radius in half? Or if I double this mass and cut this in half, what has a bigger effect? So we do need to solve using this equation, but we also need to have a conceptual understanding of how the proportionality works between force and these three variables here. Okay, thank you.